So, much like her, I don't have many fractals in this, but I have at least once, and I think I mentioned house dimension at least once. So I'm mostly going to be talking about self-similar sets and self-similar measures and how it corresponds to something called Garcia Entropy, which gives us some information about the dimension of these measures. So to begin with, let's look at the examples. They make more sense than the definition. So S is going to be a set of digits. And I'm going to have some math that goes from this set of digits to a real number. So for example, if I have digits 0 and 2, I can look at all possible infinite sums of either 0 and 2s with 3 to the minus n. A quick check actually tells you that this gives us a standard representation of the middle third Cantor set, my fractal. That might be the last one. And all points in this image have a nice property that they have unique representation. You can take some x and it's a unique representation with 0s and 2s, and vice versa. If I instead looked at digits, say 0 and 1 and base 2, the image of this is just the entire interval 0, 1. Almost all points have a unique representation. There's a small number of points that will have two representations, like a half could be 1 and an infinite number of zeros, or 0 with an infinite number of ones. Things get more interesting once the base is not an integer. For example, if the base beta I'm using is the golden ratio, then I could write 1 as 1 over beta plus 1 over beta squared, or I could write it as 1 over beta, 1 over beta cubed, 1 over beta 4, and so on. In fact, there's an infinite number of different ways to represent 1. So I've moved away from the idea of a base 2 representation where I have at most 2 representations. In fact, in this case, 1 has a countable number of pre-images. There are examples of X that are in this image that have an uncountable number of pre-images. So a Bernoulli convolution, what I'm doing is I'm actually just looking at taking some real number, looking at the set of pre-images, or in fact, in this case, take some at set E, look at the set of all pre-images of all points within E. This gives me a set of infinite sequences. I've got a nice product measure I can assign to this. The product measure of the pre-images of E is equal to the Bernoulli convolution of E. So it's a measure with respect to beta. Typically here I use digits 0 and 1. And quite often I use probabilities 1/2 and 1/2, but you can mess around with these probabilities. There's an alternate definition, which I'm not going to, I don't actually need either definition, I just need the concept that it exists. And that would be the unique measure, which has the property that the measure is equal to P naught times the measure with the pre-image of S naught and with the pre-image of S1, where they have this property that it maps it, X goes to what the X over beta, or X goes to X over beta plus 1. Okay, so I now have a concept of a Bernoulli convolution. These are all examples of self-similar measures. I will do some more general things later on with it. One of the very standard first things that most people learn in a measure theory course is what it means for a measure to be singular with respect to Lebesgue measure, or what it means to be absolutely continuous with respect to Lebesgue measure. So if it's singular with respect to Lebesgue measure, it means you can decompose the space into an A and a B, where all the measure of the Lebesgue measure is on A, and all the measure of the measure you have is on B. And if you look at the Lebesgue measure of the other, it's 0, and then you look at the regular measure of the first, it's 0. So somehow the measure of the space can be decomposed into parts where all of mu lies and into a space where all of the Lebesgue measure lies. Absolutely continuous means the exact opposite. It means that anytime I have something of positive measure with respect to Lebesgue, then I'm going to have positive measure with respect to mu and vice versa. And it's one of the early things you learn in measure theory courses. Every measure can be decomposed into a sum of these two types of measures. So it can be decomposed into a singular part and a continuous part. Turns out for Bernoulli convolutions, which I'll mention later on, this decomposition is incredibly simple. So let's think about an example. This is the Cantor set that I looked at before. So here I use digits 0 and 1 instead of 0 and 2, but it's the same sort of idea. And I can approximate what this measure means. So what I'm saying is, here I've got sort of a low-level approximation. If I take a set E, integrate it with respect to this approximation, I get a number. It's going to be somewhere between 0 and 1. And the more iterations I take of this, I get better and better approximation. I should comment here, these things are spiking along the points that are in the Cantor set. So in here, that goes all the way up to 5. So it's actually got a lot of weight concentrated in a very small amount of space. Next one, if I did a Bernoulli convolution with root 2, I can again approximate this and get a better and better approximation of what the measure is. I think I can go one more. And this actually, if you iterate this enough, this goes to a nice smooth curve. So the Cantor set was something where it spikes and concentrating on a set of very small measure. It was singular. This is approximating to a very, very smooth curve. This is going to be absolutely. If I did this with the golden ratio, again, I can do an approximation, and it turns out with a lot of work that you could show this as singular, that the approximation, you've got parts that are spiking off to infinity, you have parts that are going off to 0, and the approximation gets messier and messier, and this was a singular measure. So very early result in 1935 is, as I said, this decomposition into a singular part and a continuous part is stupidly easy. It is either singular or it's continuous. There's no decomposition. It's one or the other. And Hare in 39 said, okay, it's one or the other, and in the case where beta, our base, was a Pizot number, then it is singular. And a Pizot number is an algebraic integer greater than 1. In this case, it'll be between 1 and 2. Such that if you look at its minimal polynomial and look at all the other roots or look at the conjugates, they're all strictly less than 1 in absolute value. Garcia in 62 gave the example where we know it is absolutely continuous. So I should comment in the first case, the golden ratio is an example of a Pizot number. So this is why it showed up to be singular. Our Garcia number is sort of the opposite of a Pizot number. It's a number between 1 and 2. All of whose conjugates are strictly greater than 1 in absolute value instead of strictly less than 1 in absolute value. And in this case, the square root of 2 is a good example of this because it only has one other conjugate minus square root of 2, and both of those are greater than 1. And in this case, it's absolutely continuous with respect to Lebesgue measure. Solomniak in 95 showed that almost L beta is absolutely continuous with respect to Lebesgue measure. So these Pizot numbers is a very rare exception. It's a set of measure 0. In fact, even more was known in 2014. Schmerken had showed that the set of cases where it is singular, not only is it Lebesgue measure 0, it's Hausdorff dimension 0. So it's a really, really small set. And I should comment here that the set of Pizot numbers is a nice countable set, so it would have Hausdorff dimension 0. Dimension of a measure. This is the idea of absolute continuous and singular is something that can be captured with something called dimension. They're not exactly analogous, but they're close. So we define the measure of some u of beta as the particular value alpha where this limit equals alpha almost all of the time. It's not even clear why this would exist or why something would ever be true almost all the time, but in this particular case, for these sort of self-similar measures, this is true. There will exist a single alpha with this property. A different concept of a dimension of a measure, this is the second time I'll say Hausdorff dimension, take the set of all z where the measure has full measure upon z, and then look at the Hausdorff dimension of that and try to minimize the Hausdorff dimension of that. It turns out In this case of self-similar measures, in this case, these two dimensions are exactly the same. Another thing that's very useful is if it's absolutely continuous, then both of these dimensions, not only are they exactly the same, they're equal to 1. In the case of self-similar measures, it is not known if the converse is true. It's not known if dimension 1 means absolutely continuous. If I'm allowed to just create any measure I want, I could definitely find examples where the dimension's equal to 1 where it's not absolutely continuous. But for self-similar measures, I suspect they're the same thing. We don't know how to prove that. But it does mean that if we're going to try to find something that's singular, a good way to do this, try to find something who has dimension less than 1, or if we're trying to show something's absolutely continuous, a necessary condition, although not necessarily sufficient, is that its dimension is equal to 1. And a very recent result by Hookman in 2014 showed that both of these dimensions is basically the same thing as the Garcia entropy, or Garcia entropy or 1, whichever is smaller. So if I can get the Garcia entropy bigger than 1, I know that the dimension's 1, which means it's probably going to be absolutely continuous. But I need to define what the Garcia entropy is. So it's sort of an ugly definition. So I look at all the images of length n so I sort of think of like the length n representations of beta, look at all the images and count how many repetitions it is. This is going to emphasize how much overlap there is in a particular representation. And the Garcia entropy is this limit here. And one nice property is if I look at this value for n equals 100 or 101, it's sort of a weighted average of n equals m and n where they add up to 100 or 101. And from that, you can actually get that this limit exists, this limit exists, and this is one of the primary things that we've been looking at in the last little while. So, very old, or reasonably old result from 91 was a exact computation of the Garcia entropy for the golden ratio. Notice it is less than 1, it is singular. It's pretty close to 1, but this is exact. In fact, the method they gave a precise description to figure out what this is to any number of digits, and this was generalized later on, instead of just a golden ratio, but to the roots of more general polynomials. Remember when I initially talked about this, I typically said the probabilities were 1/2 and 1/2. In 2013, they looked at the cases, what happens if these weren't equal? What if one of them was 1/3 and one of them was 2/3? So it's more generalized techniques to deal with unequal probabilities. A slightly different example, in the original example, I always had digits 0 and 1. In this case, I'm looking at digits 0, 1, 2, up to a minus 1. And I assign them all weight 1 over a, but precise ways to do that. And a result that I published with, this is something I always like pointing out. I am the second Hare. There are 2 Hares on this paper. I have absolutely no relation to Catherine. It's just one of those strange, freaky coincidences. And alphabetically, Catherine is always ahead of Kevin. Or if we just go by initials, KE is always ahead of KG. I'm always playing second fiddle to her. I'm always second. The third person, Brian Morris, was an undergrad we had supervised for 2 summers ago from Stanford. And the fourth was an undergrad, Rosie Shen, who's graduating this year. If she applies to university, take her. She's absolutely fantastic. It was a same sort of idea in that we looked at a space where the digits was more general than 0, 1. It went up to n minus 1. And the beta we were looking as base was d. So here I'm looking at the number of representations where I have way more digits than I should for a base d representation. And we get precise computations for equal probabilities and very good upper and lower bounds when they're unequal probabilities. Work with a collaborator in Manchester, Nikita Sidorov, is the dimensions for all these mu beta, all these Bernoulli convolutions, for all piezo numbers is greater than 0.81. We know they're all less than 1 because we know they're all singular, but we didn't have a good lower bound. This we improved in 2018, and the 0.82, that improvement is not the meaningful part. The meaningful part is the first one was only for piezo numbers, which is a nice countable set. The second is for all beta in this range. So we wanted to improve the number just because it was something visible, but it was more the improvement that it extended to a much wider variety of beta. And we gave some other criteria. For example, if you take some algebraic number and you take its kth root, and if the kth root is actually of higher dimension, then we can actually get the dimension is equal to 1. And very recent work that we're working on, still to be submitted, is that if beta has some other conjugates greater than 1, then we can actually quite often say that the dimension is equal to 1 and that the Garcia entropy is strictly greater than 1. An example of this is you take some piezo number, take the inverse of every single root. So all the things that were inside the unit circle are now outside, and all the things that are outside are now inside. Since everything except one of those roots was inside the unit circle, once you invert it, everything is outside the unit circle. It appears that every single one of those will have Garcia entropy greater than 1 and will have dimension equal to 1. I think I looked at like 24,000 cases and it was always true. That's not a general proof, but it's a good computational evidence that it's the right sort of thing to be looking at. I think we're going to get a slightly more on track, because that's all I have to say.
Any question?
So, do you see some relations with these maps of the connectivity where you have multiple polynomials with coefficients 1, -1, and zeros?
Yeah.
You can also take
Yeah, these are all very similar concepts. If you have
for the real case, right? The real line, and then you can find these values in there in the antennas.
Yes, they're very related ideas. Yeah.
What is the dimension of this measure exists? The limit of the logarithm of the happier thing? It looks like the Lebesgue derivative, but it isn't.
It's actually something called the local dimension. So what it's measuring here is the concentration around a point. If it's higher than expected concentration or lower than expected concentration of the measure. And it's in no way clear that this limit should exist. It's clear that the lim sup or the lim should exist, because that'll always happen. It's not clear that it should even be finite, or it should be, or possibly that it's non-zero. In fact, but in this particular case, for all of these things, it is in fact, it's a positive finite number, and it comes out of the fact that these sort of self-similar measures are called exact dimensional. I honestly don't know the proof for that. I just know that this is a common result in this area, and I exploit this ruthlessly.
Isn't it like extracting the exponent? Like if that mu is like a volume of a ball,
Yeah.
so it's essentially extracting the exponent, right?
It's essentially extracting the exponent, and this is why it's typically called the local dimension, because it sort of feels like, what is the dimension of this measure locally around that point? And it will be different at different points. In fact, for all of these measures, if the image is say full support on 0, 1, I will have sometimes this limit will be greater than 1, sometimes it will be less than 1, but it turns out almost all of the time it's the same thing, and if it's singular, it'll be less than 1.
Questions?
Is there some kind of ergodicity?
Behind this particular result, I don't know. There's definitely some very precise results that if the Bernoulli convolution depended upon a p-zone number, I can actually normally find very, very tight bounds for exactly how high this limit could be or how low this could be. And this comes out of products of particular types of matrices, and it's all ergodic theory type of thing at that point.
Because they exist almost everywhere.
Yeah, yeah.